Hi, this is Clifford Carnicom from the Carnicom Institute, and this is the second in a series of videos and discussions revolving around a climate model software project that I've been working on. And today what we're going to do is introduce a scenario. The program handles various scenarios, and today we're going to introduce what appears to be a relatively simple scenario, and yet we can see that it can have some interesting sort of consequences and effects from some simple changes. So I think I'd like to cover a few things before we go directly to the model, and this would be to start introducing the discussion on climate change. I used to work with this topic quite a bit in the early years of my research, and I'm coming back to that for a revisit because of I think some of the confusion and either information or misinformation that isn't necessarily grounded on the science level as much as we might like it to. The climate change issue, frequently referred to as global warming in the past, and going through sort of a change in terminology there, is really as much of a political issue and a social issue, even more so in terms of how it's perceived, I think, than it is necessarily founded on some principles of science. So I think the first thing that's helpful when this issue is just discussed is to make sure that we have a historical perspective on the issue versus a contemporaneous perspective on things. If you look at climate change in terms of years or decades, and actually even centuries, it's quite a different situation than if you look at data with respect to thousands and thousands and hundreds of thousands, if not millions of years. So I think the first thing that's helpful to avoid the traps of sort of a limited view would be to be aware of the historical perspective. And in that vein, one of the first things I'd like to do is recommend a certain book that I think is worthwhile reading. And the name of this book, you'll see that on the screen now. The name of this book is called The Whole Story of Climate: What Science Reveals About the Nature of Endless Change. And one of the things that disturbed me when I started to revisit this issue is how often the information presented is in terms of recent years or recent decades. And that bothered me because we're obviously dealing with a bigger picture than that. And this book expresses that viewpoint, that the very first thing we must do is have a historical, in this case, a geological perspective. The climate change issue is not a new issue, actually. There were people working on this issue several hundred years ago, and it is not just of recent vintage. And one of the main points that this author will make, Kirsten Peters, is that the geologists have basically been climatologists from the beginning. And the more current crop of climate researchers often do not have the perspective that geologists have had for actually hundreds of years. So I want to introduce this book to you, and if you're interested, I hope you'll read it. I think you'll have a good perspective on time frames very early in the game, and it's an interesting book because it goes through the story from a standpoint of people's lives, of geologists who spent their lives observing things and often for the first time, and running into a great deal of controversy in their day in the 17 or 1800s when they started to voice their theories that were in opposition to many of the perceived either theological or sort of grand images that humans have of themselves in the overall sort of scheme of history and continuity of life. So that's our first recommendation that I'd like to make. Excuse me. The second thing is, before we again go to the model, I am putting some selected images up on the page with the model, and I'll start by going to, let's see if let's start by going I'd really like to start right here. I have some selected images here, and what I would ask is that you start to research these topics that are presented on here in an image point, from an image point of view, to start to learn what these images are about and where they come from. And I won't go through these in depth now. I just wanted to point out to you that these images are interesting in that they cause us to seek, I think, a more well-rounded picture on the climate issue. And certainly Kirsten, as well as others, will be speaking of this. That first graph you see there is ice core data. There is climate data available to us going back anywhere from 400,000 to 700,000 years. There is a lot of data available. And it's important and necessary that we look at that full scope of data before we start reaching assessments or conclusions about what might be or what might not be the case now. And this graph will show you basically temperature and its correlation with carbon dioxide levels. And again, I'm not after the more intense interpretations of this now. That'll come later. I think the point I would make at this time is that if you study the evidence and the information, the case is stronger that what we know is that carbon dioxide and the greenhouse gases, CO2 and methane, they correlate with temperature, but it would be quite faulty to state that a temperature increase is a result of greenhouse gas emission. As a matter of fact, as you may find in your readings, it's really exactly the opposite of that. The greater case is made that orbital variations over time in the Earth are largely responsible. So the point here is to say that we know there's a correlation between these greenhouse gases and temperature, but it would be, I think, quite flawed to assume that one is the source of another. So the issue of correlation versus causation is the first thing I'd like to bring up, and for you to start looking into that relationship or lack of a relationship thereof. So that's the first important historical graph that I think is helpful. We have a lot of data available. I'd like to introduce a graph here at the bottom here and introduce you to a very important name. And forgive me if I mispronounce it, Milankovic. This fellow was a Serbian. He lived at the turn of the century. That's 1900, 1890s, I think he was born. He did some of his most important work while he was a prisoner of war during World War I. He was a geophysicist, amongst other things, and he basically solved a very important problem. And he came up with his theory before the data came out to either refute or support his thesis. But he in large part explained the earlier graph that I have showed you. Milankovic understood the relationships between dynamic changes in orbital variations of the Earth on four different levels actually there, and how they would expect to produce climatic changes. It was after his death that his work has been slowly accepted and is now rather strongly accepted as explaining very well the graph that you saw earlier in terms of these variations in temperature. Also, going back to that graph, there are interesting things to notice. Number one, our current period, and again, one tick on this graph is going to be, 20, whatever it's going to be, 50, at least 10,000 years or so. One tick on this graph covers a lot of time, but you can see our point in time historically, at least from the standpoint of those climatic records, it's not anything that is actually extraordinary. It's certainly on the high end of the scale, but it's not extraordinary compared to previous times. Another pattern you'll see is the sharp rise in temperature when it occurs, short and sharp. And what this means also is that the history of the Earth is ensconced in an ice age. Really much colder conditions represent the state of the Earth over the vast history, and that the periods of warmth, extreme warmth, as we have now in a relative sense, are actually very brief and not very frequent. actually. So that would be the second thing to observe from this graph. And the third thing to observe from this graph that's interesting is notice sort of the flattening or the stalling out that's occurring, a flattening of this peak. And again, this is not a short-term graph here. You get to speak in terms of geological time and epochs and the Holocene period. You're talking about the existence of all of humanity when you're looking at this little block back here. So it's not really even quite really fair to try and limit yourself to industrial age considerations. But as Kirsten will point out, the influence of mankind and its potential effects since the beginning of history of mankind in terms of potentially flattening out that curve. It's a very interesting topic. So those are three things right away to start putting things in historical perspective. So we will introduce ourselves to Milankovitch along the way and what his work meant and how significant it was. The other thing I think on some graphs here that are important are data. Get a hold of the data. And in this case, I am expressly attempting to gather the data for recent history, meaning decades, but again being kept in context. And these graphs reveal some interesting topics of discussion. And again, we have to separate ourselves from the social or political context, but what does the data show? And that data can be with respect to temperature, which is what's being shown here. That data can be respect to CO2, carbon dioxide, and that data can be with respect to methane especially. And these are three important variables of combination that we will look at over time. Here's another graph that shows changes, and this is all very current data, changes that are happening with the ice caps. Very, very interesting in terms of, you'll see divergence, and life is not so simple as just to assume we have global warming and that's the end of the issue. It's really not the issue in the grand case here, that this is a one-way street. Another graph here prepared by a couple of meteorologists, climatologists. It's more of a graphic schematic than anything, but it's an interesting one because it shows variations of time even with respect to more recent times, being that of written human history. And it shows us that things are not constant, and either these things are often a matter of frequency and time interval considered, but this type of graph that you see here can be a blow up essentially of the very tail portion of this graph above, and you see that we get really a different perspective when we look at things in terms of different time intervals or frequencies. So this shows once again that our current status is not necessarily extraordinary with respect to even historical times, and this period down here called the Little Ice Age is a very interesting time in history. This being in the where they have 1600s, right? 1500s, medieval age area. Fascinating point in recent human history in terms of climate change. With those things being put in perspective and these graphs being available to you, which I hope you'll begin to look at, there's another graph on methane, which becomes very important in our discussion later on. And this graph here will result directly from the software model that I have developed and worked on. So, with that being said, let's start to introduce a scenario with this model. There's an earlier video to introduce you to the controls of the model, and what I would do is encourage you to play around a little bit. There are things that can be seen that are not necessarily obvious and a little bit hard to get a picture of without a computer to assist us on this. And again, the model is in development. It's starting to become a little bit more solidified, I'd say, in terms of how things stand. And a model is something that continually be improved upon. We had the introductory video on the controls and that type of thing. The thing I'd like to do today is just take a very simple scenario and show how it can become very interesting. And that is to start to examine just the greenhouse gases alone. We're going to save everything on the right side of this screen for later times. But we're going to work with just these two items, being the primary greenhouse gases, that of carbon dioxide and methane. And many of us are accustomed to, hear the words increase. We hear the words increase in CO2. We hear the increase in greenhouse gases. But one of the things that I'd like to do is open up the topic to consider both decreases as well as increases as we go along, and to sort of impress upon us that things are not always a one-way street, and they're not always constant in direction. Remember this graph, and you'll find this in Kerson's book too. Let me go back there, about how sudden these changes are. And one of the things that is happening is we're learning they can be a whole lot more sudden than anyone would comfortably like to admit. In other words, dramatic climate changes are now in evidence occurring within literally 20 years, a generation to a lifetime over a human being, of radical changes in the climate. And these changes are such that they affect really the entire population of the earth and the ability to produce food. And as you recall, the majority of time of the earth is a much, much colder place than we happen to be experiencing now. So and since we know there's a correlation, again, I'm not talking about causation, but a correlation between temperature and CO2. Again, if that's a two-way street there, then we expect that at some point things will decrease. It's not always increasing. So this model allows for that type of change to be examined. And so let's go back to a situation here, and let's start simple, and let's just boost up the CO2 a little bit. Okay, and right now the entire scenario here is relative. These are percentage. I have tried to scale this accurately to real world physics, and the model does seem to be behaving fairly well at this point. It seems to be reasonably smooth and capturing some very interesting situations. So this runs right now from plus and minus 10%, and that's on an annual base of increase of change. 10% would be quite large. Again, you want to scale yourself to small numbers and small changes as you're starting out here. So let's say we introduced, that would be a significant amount still, let's say we introduced positive change of CO2. So this is an increase relative to the current state of affairs, is what it means. There is an assumption of the Earth heating right now at a fraction of a degree per year. And the model does not depend upon that assumption being true. I could really go either way, it wouldn't matter. But to determine change, I have to assume change with relative to existing a state. It doesn't really matter whether the issue is heating or cooling at this point. So let's say we introduce some CO2 change, and that graphic will come in on the second round through. I'll try and square that away later, but what happens there? This causes an increasing of the heating of the atmosphere. Okay, and we went over this on the first video, but you're getting three pieces of information here: the direction indicated by up or down, or color, same thing; the magnitude of the change by the height of this bar, and the last piece of information, which is an interesting one, is time. How long it would take for a temperature to rise by a reference amount, in this case 1 degree of temperature centigrade. So those three things give us a sense of impact upon that particular change of increase. So we'll go back and start to learn what that does, and sure, we would like to push things up to extremes, and these numbers truly are extreme. And you'll see that that time period of 38 years now is there, which is absolutely extreme amounts. When you read these changes below, that each degree is roughly a 15%, can be up to a 15% reduction in crop yield. So that would be very serious business, obviously. So these are not the kind of numbers you want to be working with in most cases, but that the model is meant to accommodate a reasonable range of examination. Okay, and the other thing, notice if you had a very small amount, somewhere in there, like 0.3, even 0.2, let's say we put in just a little bit. And so what you'll see there is that it is heating it up, but it's very, very slow, and it's so small that it's not kicking the numbers in, but the time frame is coming in at 44,000 years. So, and actually I want to boost it up one notch to see that flip over for you. And let's flip it up to where that number goes somewhere in between. And we're almost there. There we go. Okay, and then so you'll see that's down to 5,000 years, right? All right, so that's a fairly elementary case, but an important case of an increase in CO2 by itself and its expected impact to increase the temperature of the atmosphere. Same thing in reverse. What if CO2 were not to increase but decrease? What would we expect to happen? What we expect to see in this case is that the cooling of the Earth will begin if we decrease the carbon dioxide. So we've set that at a minus 1.6, and we see that cooling effect. Now, and this is because of the lack of that gas to hold that heat. Again, we're not talking about causation, separation between causation and correlation here. Now, the change in CO2 concentrations, both increasing and decreasing, is not a trivial issue. There is an article out by the University of Purdue, which is on your screen there, which is very interesting, basically saying that that drop in CO2 as it occurs is a harbinger of an ice age. And the numbers that they give here are that when the CO2 reaches a certain level, namely about 600 parts per million, it's currently at about 400 parts per million. When it reaches about 600 parts per million, they have correlated that as a turning point in the graph that I was showing you earlier, where you have the sudden drop off. And when you have that drop off, it begins to induce the ice age. So, and also at the current rates right now, roughly, it's rising about 1.5 parts per million. So it's on the order of roughly about 130 years or so before that 600 parts per million threshold would be reached. If you see a couple lines here, this is an interesting article. Let's see if you can get the title there. Drop in carbon dioxide levels leads to a polar ice sheet with Purdue University. Okay, the statement there is that the onset of Antarctic ice is the mother of all climate tipping points. So this would be something to be watching for, would be changes in the ice caps. And you also see here that they say the team found that the tipping point in CO2 levels for cooling that initiates ice sheet formation is about 600 parts per million, understanding that we are at about 400 right now and rising at about 1.5 per year. So we're not talking about a real long period of time before that would be reached. Now, interesting, on the other graph that was there on the ice sheets, the most current data that's being shown here from NASA right here is that the ice down in Antarctica is actually increasing, and it's fairly significant. If you see what they're saying here, the Antarctic ice extent is the largest on record, and the Arctic ice continues to decrease. So you have a divergence taking place between the ice sheets, between northern and southern latitude. So it's a very interesting observation that the ice sheets are actually increasing, which indicates potential cooling taking place. And also the temperature graph here, also the most recent data, shows a very interesting pattern of the temperature actually leveling off for the last close to 20 years there, at least 15 years, almost flattening out up here. So the claim of continuing warming is not necessarily as strong as we might think, and we can almost to a certainty predict that another radical change will occur, and that will flip the Earth into the Ice Age, a state of affairs that it's actually more commonly in. And at the current rates of projection from the Purdue study, that's not necessarily a long period of time. And it's expected that there would be increasing heat during that period. If you recall this graph right here. In fact, we are lower than the previous sessions, if you see that, also in terms of the sharpness of that peak. Now, going back to the model, let's introduce an even more interesting situation. And this is the question of offsetting influences. Let's say we reset this, and now let's go with the prospect of the CO2 increasing. And I will set that at a fairly high amount for a certain scenario that I've written here. Let's say we set the CO2 increase at a fairly high level of 5% there. Now, instead of having a singular effect here, let's offset this. Well, before we do that, have that reference value as a point of reference about what happens, and that's a very large effect, right? A 70-year turnover point for the 1 degree level, if you see that down here. All right, so the other simple case is that we increase the methane also. Now, methane is a much more powerful greenhouse gas in a relative sense, and this is by unit mass, okay, by mass concentration levels, and so that has to be factored into account. Methane is far more influential as a greenhouse gas, but there's also far less of it. In fact, the ratios there are roughly, and they're significant, the ratios are the CO2 levels are roughly at 400 parts per million, and the methane levels are at 2 parts per million. So you have roughly a factor of 200 in concentration. So that's an extremely important factor to include in the model here, and I've done that. So now, instead of having just CO2, the other simple case is just to have increasing methane as well, and we'll keep that number smaller in a proportional sense. And that was at 0.9, and then you see it jumping pretty much way up the charts at 3%, and you're down to pretty much astronomically short numbers here, or preposterously short numbers, I suppose. Actually, not preposterous when you look at some of the changes that have actually been recorded. Sudden climate change can occur, has occurred, and is expected to occur. All right, now let's go to the question of offsetting. Let's say you had an increase in one gas and a decrease in another. Let's start with that high level of 5% in CO2 so we have something to work with. Now, we know what happens at 0. Okay, we have our reference point. We have our reference point at, and we do have to pay attention to the numbers here, at 0.98%, if you see that. Okay, there's our reference value. Now let's start, instead of increasing the methane, let's decrease the methane concentration. Remember that it is a more powerful greenhouse gas, what they call global warming potential. So we're not dealing with the same magnitudes here. And let's just introduce a little bit here and see what happens. And so we see that drop. It went, if you see here, it went from 0.98 to 0.92. And the time scale would have also changed with that. We expect as we cool it down that the time frame to raise that temperature will increase. So we'll see this number increase. We'll see the bar drop. We'll see the bar go to the right to require increased time, and we'll see the bar diminish in time. Okay, so we see that effect taking place. Now, there's an interesting situation that starts to occur. Let's step it up a little bit more. Let's go to, say, 0.1. These are fairly small numbers, as we see. Okay, 0.1. And same thing, it's dropped down. It's just about half now of what it was. 0.47, we see our temperature going to 148. Or I'm sorry, number of years going to 150 years roughly. And so it's starting to have an effect on diminishing that heating influence of CO2. So this is a counterbalancing force. Okay, let's go to 0.15. You have to be sensitive and careful with your numbers here to pick up what I'm leading to. Okay, now we're down to roughly a fourth of what it is, and your time is up to 300 years to make that 1 degree difference. So the effectiveness of the CO2 has been offset. All right, let's come into some other numbers that I've sort of looked at ahead of time for us so we don't take the time to do it. Let's get up to about 0.19, somewhere in there, 196, somewhere in there. And we see that we're getting very close to a balancing point, basically. We're extending out to over 1,000 years now, and we're at a fraction, really, of a percent of where we were to originally. And let's find that 0 point, and we'll find that 0 point in this particular case, it varies with every scenario, but this particular case, that scenario will be at about, let's see if I have that in my records, roughly about 2:1. Okay, right at this point we have a pretty much 1-to-1 match with the heating effect, and it's been neutralized, and you'll see that your time went out to 150,000 years. So what this says is that if the methane levels were able to be decreased, that you would expect that the, quote, issue of global warming could in itself be mitigated to some degree. So in one sense, there's a rather important strategy that's developing here in this work of essentially it raises the specter in question of managed methane decrease, if such a thing were possible, to offset, at least in part, the impact of a heating Earth from the greenhouse gases. Now, the very interesting question here, do we have any evidence that methane could decrease or has decreased? And if you recall the introduction I gave to you, some of the graphics that I'm hoping you'll look at again in more depth, there's some very interesting things happening here. And that is that the data does show, in fact, that over the last couple decades or so, it started here, it looks like around 1985, 1890, that the growth rate of methane, the concentration is still increasing for a period. You see that lag or leveling off, but the growth rate is decreasing. Okay, so there is direct evidence that the methane levels, that rate of increase actually has decreased over the last couple of decades, and that decrease in the growth rate is exactly what we are simulating in this model. That's what those sliders are controlling, are growth rates. Not concentrations, but growth rates. This is all about change. Not only that, if you pick up the most recent data that I've been able to find, you see the same thing continuing, at least on this is linear regression there. But in fact, the methane levels have been decreasing for the past couple decades. And this says, and this suggests that in fact one would expect the temperature of the atmosphere on the Earth to actually be stalled out to some degree. And as a matter of fact, that's exactly what this data starts to show. Again, this is the most recent data that I can find, and very, very interesting that you have direct evidence of stalling out of that temperature rise. Much more dramatic here in the 1970s through 1990. So the claim that everything is automatically in a heating mode and things are always increasing is not borne out by the evidence. And if you look into this methane issue, you're going to find a parallel with CO2 issue later on in subsequent discussions. But the primary reason that is attributed to the decrease in the methane growth rate is the shutting down of leaking natural gas pipelines. These are real issues, that the magnitude of these things on a global scale, particularly in the mining operations, are now known to be the most likely source of controlling the current methane situation. This is not about locked up ice methane in the oceans. This is about methane that's already being released and being measured now under the current circumstances. So it's not only a possibility, as the model demonstrates, but the data shows that it is actually happening. And the CO2, in contrast, if we look at this data, we see that it continues to rise, actually slowly increasing even in its rate, but roughly 1.5 parts per million per year. So the question of offsetting is a very interesting one. Also, if you remember the stalling out, now you'd never pick up that type of thing on this graph here on this time scale, but the stalling out of the heating rate over the last 10,000 years is also an interesting prospect that is potentially tied in very much with human activities on a longer scale than just our current generations. Okay, back to the model. Now, let's continue this. Let's continue this reasoning. There is a balance point that has been found for a certain ratio of the concentration levels of methane and really the growth rates, the methane and CO2, to neutralize the heating. Now, what if you were to continue that process and continue to decrease the methane concentrations? What happens then is you do start to flip over into a cooling mode. And this would make sense also. You pass the 0 point and then you start to cool things. And we start to see a shift there where we're cooling things down again after this relative level of 1 degree, and we have a certain time frame. Now, what gets very interesting here to me is that you could view this as a strategy that can be used to mitigate global warming, but there's limits to what is realistic, let alone external influences on a grander cosmic scale that eventually overwhelmed any attempts to try and manipulate this situation. But nevertheless, within the confines of the model discussion here, there's a problem that would come up in that this is not a completely manageable situation necessarily, because as you're decreasing the methane, you have less and less of that methane to be available to use as a compensating factor. So there's a point of diminishing returns. And the question is whether or not there is actually a maximum that can be found. And that's an interesting sort of mathematical situation that developed within this model. And indeed there is a maximum. And I'll demonstrate that to you here briefly. We're at -2. Let's go ahead and start increasing it, or decreasing basically, the concentration. And let's get up to about 0.4, somewhere in there. Okay, and now we have a significant cooling effect taking place at this level. So we've skewed over onto the other side of the seesaw, and things are cooling down very rapidly now in this situation. That maximum in this particular scenario with these, this particular model, and how things have been set, is reached at a certain place, and the number happens to be 0.65 roughly. Okay. Now, what happens there then is that you have a maximum cooling effect coming into play here at that concentration level. So you've tipped the scale over the other way, things are cooling down very quickly. But remember that we're also losing our methane as we decrease the concentration. So this is a local minimum, what's called a local minimum. And then if we continue to decrease, we will see that we will actually start to head towards the heating side again. Okay, and now we're not there right now, but our maximum was at minus 0.84%. Let's go back, and we'll bring us up to about 9. And you see that it is starting to approach the 0 point again. And that 0 point is going to be, and I can save a little bit of time for us here, 1096. You once again reach that balance point. So you have two neutral points in this scenario. One when you first neutralize it, then you reach a maximum point, then you start to go back up the other way, and you reach a balance point again, and then from then on it starts actually heating again. You've lost your methane. You have no ability to cool things down anymore because you've lost it. And the graph down here below shows this visually, what has just happened here. These 2 points right here are the balance points. This point down here is the maximum. And then the phrase runaway greenhouse effect is a very valid phrase, because you'll see in this case, at least in this model, that temperature, once you reach that pivotal point, that second balance point, the heating effect will just pretty much explode. So there's interesting propositions here that are borne out by field evidence that this decrease in methane is happening. And it would seem to me that if you're actually trying to manage this situation of mitigating global warming, that the most desirable part of the curve to work in would be right in here somewhere. You certainly would not want to be anywhere near the maximum, and you'd have little effect out here. So it seems to me that the optimum part of this curve would be right in here. So this is this would be serious business, is what it amounts to. Very serious business. And any time, and this starts to raise the issue of manipulating human beings, manipulating or adjusting the climate. It's very dangerous and very risky business in general. And this model starts to show what some of that risk can be if you reach a point of no return. So there are potential benefits here that could be realized. If you had the mines, the leaking natural gas mines shut down, that could offset and mitigate global warming. That's real. But you also have inherent risks that human beings have a history of thinking they can regulate and control, and I don't know that we can claim success on that. We know that on a longer time scale that the graph down here is expected to be followed. And so at some point on some scale, that ice age, that severe ice age, says that it's coming. And it says that we are in a very unusual point in history. That's all I want to cover for this time. And it shows you that even with only two factors in this model being considered, that very interesting situations develop, as well as strategies can develop that potentially could be beneficial, but it also shows the element of risk that is introduced when both we modify as well as attempt to compensate for changes in the atmosphere. And this was especially the case as we enter into discussions on deliberate introduction of aerosols into the atmosphere for various goals and strategies. So thank you very much for your time today. I hope you'll start to play around with that model a little bit and see if some of those scenarios make sense to you. Again, it is a model, so it's only an approximation to a portion of the situation, and is always subject to change. But these discoveries of how this behaves have only been revealed, at least on my side, by the use of this model. So thanks very much, and have yourself a great day. And I'll talk to you again, and we'll try to flip over onto the topics of aerosols being introduced. Bye-bye now. There were people working on this issue several hundred years ago, and it is not just of recent vintage. And one of the main points that this author will make, Kirsten Peters, is that the geologists have basically been climatologists from the beginning. And the more current crop of climate researchers often do not have the perspective that geologists have had for actually hundreds of years. So I want to introduce this book to you, and if you're interested, I hope you'll read it. I think you'll have a good perspective on time frames very early in the game, and it's an interesting book because it goes through the story from a standpoint of people's lives, geologists who spent their lives observing things and often for the first time, and running into a great deal of controversy in their day in the 17 or 1800s when they started to voice their theories that were in opposition to many of the perceived either theological or sort of grand images that humans have of themselves in the overall sort of scheme of history and continuity of life. So that's our first recommendation that I'd like to make. Excuse me. The second thing is, before we again go to the model, I am putting some selected images up on the page with the model, and I'll start by going to, let's see if the one, let's start by going, I'd really like to start right here. I have some selected images here, and what I would ask is that you start to research these topics that are presented on here in an image point, from an image point of view, to start to learn what these images are about and where they come from. And I won't go through these in depth now. I just wanted to point out to you that these images are interesting in that they cause us to seek, I think, a more well-rounded picture on the climate issue. And certainly Kirsten, as well as others, will be speaking of this. That first graph you see there is ice core data. There is climate data available to us going back anywhere from 400,000 to 700,000 years. There is a lot of data available. And it's important and necessary that we look at that full scope of data before we start reaching assessments or conclusions about what might be or what might not be the case now. And this graph will show you basically temperature and its correlation with carbon dioxide levels. And again, I'm not after the more intense interpretations of this now. That'll come later. I think the point I would make at this time is that if you study the evidence and the information, the case is stronger of science. So I think the first thing that's helpful when this issue is just discussed is to make sure that we have a historical perspective on the issue versus a contemporaneous perspective on things. If you look at climate change in terms of years or decades, and actually even centuries, it's quite a different situation than if you look at data with respect to thousands and thousands and hundreds of thousands, if not millions of years. So I think the first thing that's helpful to avoid the traps of sort of a limited view would be to be aware of the historical perspective. And in that vein, one of the first things I'd like to do is recommend a certain book that I think is worthwhile reading. And the name of this book, you'll see that on the screen now. The name of this book is called The Whole Story of Climate, What Science Reveals About the Nature of Endless Change. And one of the things that disturbed me when I started to revisit this issue is how often the information presented is in terms of recent years or recent decades. And that bothered me because we're obviously dealing with a bigger picture than that. And this book expresses that viewpoint, that the very first thing we must do is have a historical, in this case, a geological perspective. The climate change issue is not a new issue, actually. Hi, this is Clifford Carnicom from the Carnicom Institute, and this is the second in a series of videos and discussions revolving around a climate model software project that I've been working on. And today what we're going to do is introduce a scenario. The program handles various scenarios, and today we're going to introduce what appears to be a relatively simple scenario, and yet we can see that it can have some interesting sort of consequences and effects from some simple changes. So I think I'd like to cover a few things before we go directly to the model, and this would be to start introducing the discussion on climate change. I used to work with this topic quite a bit in the early years of my research, and I'm coming back to that for a revisit because of, I think, some of the confusion and either information or misinformation that isn't necessarily grounded on the science level as much as we might like it to. The climate change issue, frequently referred to as global warming in the past, and going through sort of a change in terminology there, is really as much of a political issue and a social issue, even more so in terms of how it's perceived, I think, than it is necessarily founded on some principles of that. What we know is that carbon dioxide and the greenhouse gases, CO2 and methane, they correlate with temperature, but it would be quite faulty to state that a temperature increase is a result of greenhouse gas emission. As a matter of fact, as you may find in your readings, it's really exactly the opposite of that. The greater case is made that orbital variations over time in the Earth are largely responsible. So the point here is to say that we know there's a correlation between these greenhouse gases and temperature, but it would be, I think, quite flawed to assume that one is the source of another. So the issue of correlation versus causation is the first thing I'd like to bring up, and for you to start looking into that relationship or lack of a relationship thereof. So that's the first important historical graph that I think is helpful. We have a lot of data available. I'd like to introduce a graph here at the bottom here and introduce you to a very important name. And forgive me if I mispronounce it, Milankovic. This fellow was a Serbian. He lived at the turn of the century. That's 1900, 1890s, I think he was born. He did some of his most important work while he was a prisoner of war during World War